Hello and welcome to this lecture on harmonic oscillators. I believe this might be lecture number 3. I always have a problem remembering the particular order of my lectures. So in this lecture what we're going to be doing is to look at simple harmonic motion and to solve it using the technologies of differential equations, particularly the technologies of linear homogeneous second order differential equations. So I will take you through Newton's laws and through the solution method. So we will set up the equations and solve them by hand. We will get something called the characteristic polynomial equation, and depending on how those looks, in the case of a simple motion, it's very simple, we will get the general solution of the equation. And then we will get particular solutions by imposing initial conditions in the equation. And then we will look at something very cool called phase space. So it turns out that the dynamics of a system can be summarized in pictures of the parametric equations that the solution describes. So if you build a parametric equation with x of t and x prime of t, that will be your phase space trajectory. And that's extremely important for your projects that you should be start to considering now. So after that, we will be looking at the damped harmonic oscillator, which is the harmonic oscillator with a friction term. And again, I will set up the Newtonian solution, the Newtonian system of equations, the solutions, writing down the characteristic polynomial, and then distinguishing between three cases: the critical damping case, the overdamped case, and the underdamped case, and look at the phase space plots of that. Again, as always, I will make a combination of solutions by hand and by computer. So without further ado, let's begin. So let's see here, I guess. So let's call it simple harmonic oscillator. You might wonder, right, why it is that we study harmonic oscillators. And the truth is that we study these systems, or these systems in fact became relevant, because we see the world around us and we see that everything is oscillating. So you can really clearly see, for instance, if I hammer in the table, I don't know if you can see, but the camera is bouncing a little bit. So if you have a system that is in equilibrium, right, and you perturb it a little bit, if that equilibrium is a stable equilibrium, then as you perturb the system out of say if the equilibrium is stable, you put your solution at the stable equilibrium point. You initialize the solution at that point. It's gonna be staying there forever. It's not gonna change. But if you perturb it ever so slightly, it's gonna happen something like it's happening here with my camera, right? So if I move my table, I don't know if you can see. Let's see. Yes, did you see it? I move my camera and my image kind of fluctuated. So my image the pixels move up and down. And it had a motion like this, and then it kind of stopped. That motion we will be able to describe mathematically. Electromagnetic fields are oscillating, oscillating waves that oscillate in space and time. So electromagnetic radiation, your Wi-Fi signal is a wave that is described by equations very similar to the harmonic oscillator equations. Any dynamical system, any particle moving in a force field will verify that. So if you have, like, say, a planet, right, it's orbiting a star, and then a huge asteroid flies by, well, it's kind of gonna perturb a little bit the planet. So the trajectory, that circular trajectory, is not gonna be circular anymore. It's maybe the radius is gonna oscillate a little bit with time, right? So the planet that was having constant radius of orbit as a function of time, now the radius is kind of fluctuating. So harmonic motion is everywhere. To give you an idea of this, I have a very respectable and very nice physics professor. He taught me what was called back then advanced quantum mechanics, third year. He told me that about 50% of all physics is harmonic oscillators. So make no mistake, the quantum field theory is a bunch of harmonic oscillators. a lot of stuff that we see. If you are to understand lasers, for instance, the way we understand lasers is like the atoms, right? They are oscillators, right? And the laser is a forcing field. And then you kind of like tailor that forcing field in such a way that, there is stimulated emission of radiation. So as those electrons move between the levels, right, they emit new radiation that stimulate new emissions in new atoms. So whenever you have a charged particle that oscillates, so any accelerated charged particle will emit a radiation field. That radiation field will have the frequency of the oscillation of the charged particle. So if it encounters another charged particle, it's gonna absorb the field and oscillate, and that new charged particle that is oscillating, it will emit a new electromagnetic field. So, a lot of physics is harmonic oscillators. What a big, what a big like monologue for a lecture that nobody watches. Or, you will watch like in 5 weeks after the course ended. So these equations are derived from Newton's laws. So Newton, told us that force is equal to mass times acceleration. These are vector equations anyway, but in one dimensions. In 1D, what you have is a single line, right, of a space, right? And then, physical particles, objects, move along that line back and forth or back, according to this law, right? So the acceleration, right, it turns out that it's the second derivative of the position with respect to time. And the force is called, minus k times x. This is called the elastic force. And some people call it restoring force. It's great because at x equals 0, then the force is 0. And then the acceleration is 0. And then the speed is constant. Or the velocity is constant. So at x equals 0, what we have is an equilibrium point, right? If I put my particle here and I let it be there at x equals 0, and the initial value of the position at t equals 0, the particle is there, it will stay there forever. Because if you put it there at position 0 with velocity 0, the acceleration is also 0. So, the velocity will be 0 forever. But if you put it here, then x is larger than 0. So the force is less than 0 if k is larger than 0. So then the particle is going to be accelerated in that direction. So if I start the particle here with 0 velocity, it will go like that. But, it will accelerate here. But of course, once it gets to that point, x equals 0, then the acceleration will be 0 again, because the force is mass times acceleration, and at x equals 0, the force is 0. So then it will overshoot, and it will go all the way through here, and then it will go back. And an harmonic motion does that forever. So when x is larger than 0, then the force is negative, and the acceleration is negative. It means the particle accelerates that way. When x is less than 0, then the force is positive, and the acceleration is positive, and the particle accelerates that way. But this is a differential equation, because that's the second derivative with respect to time. So let me write that differential equation. Force, mass times acceleration is equal to mass times the second derivative of the position with respect to time twice, and is equal to the force, which is minus kx. So then once you have that equation into your head, then you know that you are done, because what you have divided by m, what you have is x prime prime plus k over mx equals 0. And that's your solution. In practice, people call omega naught squared k over m. And that's called the natural frequency of oscillation, for reasons we are gonna find. So in the end, the equation becomes x2 prime plus omega naught squared x equals 0. Second order, homogeneous, linear, autonomous. non-separable, non-easily separable, right? So that is second order. It means that, our solutions are gonna be x equals x of t. That will represent the displacement with respect to the equilibrium position. In this case, it's trivial because equilibrium is at 0. In principle, you might, change this force and put here minus k x minus some x naught, which will be your new equilibrium position. But you don't need to worry about that. We can assume, without loss of generality, that the equilibrium position that we are using to model our oscillating system, that equilibrium position is at x equals 0. And it doesn't matter where we put x equals 0, so it's general. The equation is second order. It means that that will be your dependent variable. T is time, and is your independent variable. Omega naught we know, but it's second order, so we need two initial conditions. So we need x of 0, which I'm gonna call x naught, and x prime of 0. Now the derivative of x with respect to t is the velocity, so I'm gonna call it b naught. So this is the initial position, or the initial displacement, if you want, from equilibrium, and this is the initial velocity. So that is the equation, right, that we need to solve. It is pretty interesting, right? It's your kind of prototype of second order homogeneous linear differential equation. Is the prototype for that. And in fact, everything that you learn when you solve this equation is immediately transferable to third order homogeneous linear equations, to fourth order homogeneous linear equations. The concepts are the same. So people, of course, study this equation because it's the simplest prototype of homogeneous linear equations of any order. So you can study this whenever you want, and if you study this, you will know your linear homogeneous differential equations. In fact, you should have also an x prime term. That's the damped case. So once we include, imagine that the oscillating particle is going to be dragged, right, by a medium that is kind of pushing back on its motion, then you will have an extra term in the equation. That's a drag term. So we will look into this, into the details of this in what follows. So with these ideas, we can already start to solve the equation, and you will see how this characteristic polynomial equation emerges. But let me first show you very quickly how to translate this equation into some other type of equation. What is gonna happen is the following. Look, what I'm gonna assume is a solution. It's gonna be what we call an ansatz. Means guess in German. And what we are going to be doing is to assume that our solution x of t is some constant times e to the rt. Right? We are going to assume this. And, our equation is this equation. Right? So, of course, we will see what happens when I plug this into my equation. And this is my equation. It's the harmonic oscillator equation. So let's plug in this x of t into the equation. So I have to compute x prime of t. So given x of t, x prime of t is gonna be r times a e to the rt. Right, if you take the derivative with respect to t of this function, you are gonna get this, that is r times x of t. So, and r is a constant. And actually, I'm gonna assume that it's gonna be a complex number for the time being. It can be real or complex, doesn't matter. So x2 prime, right, of t is the derivative with respect to t of x prime of t. Right. And x prime of t is rx of t, so that is the derivative with respect to t of rx of t, which then becomes r is a constant, the derivative of x with respect to t, which is rx prime. But x prime is rx, so that is r times x. So that is r squared x. So now I have my equation. It has become something else, right? What I did is to introduce this, and what I got is the following, right? Is the following. x2 prime is this thing, and that thing is r squared x. And then omega naught squared x. And that is equal to 0. So you can see, right, that I can pull a factor x out. And because x is different from 0, the only possibility is that r squared plus omega naught squared is equal to 0. This is called the characteristic polynomial equation. And this is what we learn. What we learn is the following, that if x of t is equal to a times e to the rt, then our harmonic oscillator equation, which is this equation, it is satisfied provided that r, this r here, satisfies this equation. So if this is true, then this implies that. So if r satisfies this equation, then x of t equals to e to the r a times e to the rt is a solution. So let's calculate r. R squared plus omega naught squared is equal to 0. So r squared is equal to minus omega naught squared. So r is equal to plus minus, can take two values, the square root of negative omega naught squared. If you know your math, omega naught square root of negative 1. So this is plus minus I omega naught. Therefore, x of t can be this thing. So there are two possible x of t's. These are called linearly independent solutions. And the general solution of that differential equation is a linear combination of linearly independent solutions. So the general solution of x2 prime plus omega naught squared x equals 0 is x of t equals to a plus e to the plus I omega naught t plus a minus e to the minus I omega naught t. We need to find a plus and a minus, right? How to do this? Well, we have the initial conditions. X of 0 is equal to x naught. So you have to put t equals 0 here, so a plus plus a minus is x naught. And then v naught, x prime of 0, is v naught. And that's equal to I omega naught. And then a plus minus a minus. Cool. So we have our solution almost. So we need to solve for a plus and a minus now, a system of two equations with two unknowns. So a plus a minus is equal to x naught. A plus minus a minus is equal to v naught divided by I omega naught. So what are we what are we gonna get in here? It's getting complicated. If we add them together, right, we get 2a plus just by adding both equations together. 2a plus, this go away, x naught plus v naught I omega naught. So in a minus, you have to subtract them. Then you get 2a minus equals to x naught minus v naught divided by I omega naught. So we have found a formula for a plus minus, both of them at the same time, is 1/2 x naught plus minus v naught divided by I omega naught. We found the a plus minus. And now we find our particular solution. X of t is equal to 1/2 of x naught plus v naught over I omega naught e to the I omega naught t plus a minus, which is 1/2 of x naught minus v I omega naught e to the minus I omega naught t. And you can see it's kind of getting very complicated. It's kind of getting very complicated. It's like the simplest homogeneous linear equation that there is. This is it, right? There is no simpler equation than this equation here. It's the simplest there is, right? And look at the analytical work we are doing, right? It's brutal, right? It's a brutal analytical work that we are doing, right? And this is the simplest. It gets much more complicated the harder it is. But if you want to really prove the thing, that's what you have to do. There is no other way around it. Now, there are a couple of formulas that will prove handy. Sine of x is equal to e to the ix minus e to the negative ix divided by 2i. So you can see here we are going to get sines, and here we are going to get cosines, right? And cosine of x is equal to e to the ix plus e to the minus ix divided by 2. So we are going to get sines and cosines from here. So I'm going to use those stuffs in here. So x of t, x naught common factor, and then we have e to the I omega naught plus e to the minus I omega naught divided by 2. The next one is to take a common factor v naught I omega naught. V naught omega naught. And then I have a 2i dividing and e to the I omega naught t in the numerator minus e to the negative I omega naught t divided by 2i. So now you have that x of t is equal to x naught cos omega naught t plus v naught over omega naught sine omega naught t. And this is our general solution. Right. Let me write it here in its full glory. We just finish the page. X of t, x naught cos omega naught t plus v naught divided by omega naught sine of omega naught t. That's our general solution. That is the function that satisfies the equation. That's the particular solution of x2 prime plus omega naught x equals 0 with these initial conditions. This equation have that solution. So let's see if I can actually animate this. I have to take care that there is nothing too embarrassing here. So I'm gonna go to the Wolfram Cloud and see whether I can animate this. Let's see. Hey, there it is, but you know, it's not with the right Luma key. No. Yeah, I kind of forgot which color correction. Apply LUT is the LUT. Yes, apply LUT. Browse. Invert. Okay. Hey, I made it. Sorry about this. I have to do these things on the fly. Look at all my tabs in there. It's so embarrassing. So let me go sign in to the Wolfram Cloud and let's solve that equation. So I'm gonna put omega naught. So if you type escape omega with capital escape, you can put it like this, omega. That I'm gonna call it, it should be little omega. So escape little omega, escape. Now to put a subscript, unfortunately, I don't think I can do it. No. So I'm gonna call it omega. I'm gonna set it to 1 for the time being. Yeah, that's the only parameter. And our equation is gonna be the following equation. It's gonna be x2 prime of t plus omega escape square times x of t. So that equal to 0. That is the equation. Let me increase the magnification so you can see it well. Yes, a huge magnification. Let's get rid of this. Then the next is the initial condition. And then the next is the initial condition for the velocity. And I cannot put subscripts, unfortunately, here. I want to put solve for x of t as a function of t. And I'm gonna solve this, I'm gonna call it disp of t, like this. With this you define a variable, so a list of equations. Why? Equations or lists of equations. Ooh, let's see. So I'm gonna get myself an example with an initial condition. So this is almost the same, right? Look. I probably broke it. Yes, because now x prime of 0 has been made equal to b naught. So I'm gonna have to go here. So now it's not working. So here is the quit kernel trick. So, you know, if things... So essentially here I put an equal sign, right? And it should have been a conditional a conditional equality like this one, double equal sign. So when I put an equal sign, this symbol got to be used as that symbol. So essentially we are getting true there. So if I put this, it's gonna work. And you can see the solution. Exactly what we got before, right? So now we have also to maybe put x naught and b naught and stuff like that, right? So yeah, in fact, you know, we can change omega and just keep it like this. And maybe even like put it as a function of omega. Escape omega escape with underscore, a function of x naught with underscore. Hey, no. A function of x naught with underscore, and a function of b naught with underscore. So like that. So now, for instance, I can go and plot a disp of x for different values of omega. So I can put omega 1, 1, and 0 for the velocity, and do that between -2 and 2, between x of t, between 0. Now, this means that the period is 2 pi, so I'm gonna put 2 pi here. Maybe 4 pi, so we can see 2 periods. Right, so we see 1 period, 2 periods. If I manipulate the plot, then you can see the effect of the different parameters. So I'm gonna put here these parameters, but I'm gonna have to take the underscores out. Right. And here I'm gonna put those parameters again with the underscores out, but you have to do it. So omega, I'm gonna vary it between, I don't know, very small, 0, and maybe 2, so you can see what happens. X naught, I'm gonna vary it between 1 and 3. And V naught, I'm gonna vary it between 0 and 2. And then what we're gonna get is a kind of little box. Oh, let's put it in here. I forgot this stuff here. Put a comma there, and now it is there. So if I go here, you can see that I have the manipulate object with some sliders, right? So probably I'm gonna have to make it a bit smaller so you can see it. Take this out, maybe. Decrease the magnification to 200. Sorry about that. And you can see it in here. Probably I should move myself out. Let's see if I can move myself out. So now I have to look this way to point, right? But yeah, in here we have this, and you can see those sliders in there. So I'm gonna move those sliders to tell you how this thing changes. So essentially, you know, changing the frequency. It's not changing. Oh, you know, because it has been defined before. So let me clear W. You know, I can call it, instead of omega, I'm gonna call it W. Because now it has been defined before. At the beginning, I put omega equals 1. Ooh, so I'm gonna call it W, you know. I'm gonna call it W because I think that it's not gonna work, so I'm gonna do that. Yes, now it's better. I'm gonna put here a W instead of an omega. It doesn't matter if you haven't read. You know what happened is I defined omega before. Now you can see it's not showing, but if I put omega here, yeah, I should put omega from 1 to 2. Right, so it's better like that. So if I increase omega now, the frequency increases, the period becomes smaller, right? You can see that. What about if I change the x naught? Well, I'm changing the amplitude. Just look at the axis, right? It's only the axis that is changing, right? It's the initial value that is changing. So it's like a scale transformation. And look, if I put v naught, right? I'm kind of like shifting it horizontally. Right. So essentially with v naught, you are changing the slope at 0, right? So we can put a larger v naught, maybe a slope. I think the highest slope is, let's put 5. Let's see what happens. The amplitude also changes, but it's mostly a shift. Changes the amplitude as well. And x naught, you change it. And then with W, you increase the frequency. Right. So that's the way it is. And you can do this now on your computer. Remember, right, if you are watching the classes, if you want to extract something of use in your life from these lectures, you should do this. Because doing this, it will help you very quickly understand what that means, what that means, what that means. What is omega, right? What is the frequency? What is the period? Well, 2 pi over omega. You have all those things that happen. So I think because I've been like talking very much, and we solved the equation. There is, however, one extra thing I wanna make before I let you go. No, I didn't want to vanish. I want to stay here. I want to, yes, go back to my thing. So I'm gonna go maybe here in this corner, and I'm gonna start from the top again, like this, and discuss with you the notion of phase space. So I'm gonna go here in this corner and discuss the notion of phase space, but I'm gonna not put myself in the middle, so egocentric. I'm gonna put myself in the corner, change a little bit the color, maybe a magenta, some kind of pink. Let's see if it works. Because there are so many color and images, so I have to test whether the color works. If I put green, I don't think it works. Let me put green just for fun. This is green. Yeah, it's not showing. I'm writing insults here in green, but no, it doesn't show. So green doesn't show, but this magenta shows. So essentially what we're gonna be doing now is to discuss the notion of phase space. X of t and x prime of t, you can call them x and x prime and think about them as dynamical variables. And you are gonna be looking at some vector. I'm gonna define a vector. I'm gonna call it x like this. And I'm gonna put in the first column of that vector, or maybe I'm gonna make a row vector like this, right? A point in a space. The x component of that point will be x, and the y component of that point is gonna be x prime. And that vector or that point is a function of time. So now you are imagining a new space. We are gonna call it phase space. It's a two-dimensional space for the harmonic oscillator. The x-axis is x indeed, but the y-axis, Dave, is not y, is x prime. Whenever you have a point like this, if you took Calc 2, this is called a parametric curve. So you can see you might be at t equals 0, right? That will be the point x naught v naught. And then that is going to change as a function of time. Right. So what would be the shape of this parametric curve? The trajectory in phase space. So this parametric curve is also called phase space trajectory. So I have my solution. My solution x of t is equal to x naught cosine of omega naught t plus v naught over omega naught sine of omega naught t, according to my brain. Let's check the dimensions. This has dimensions of length. This has dimensions of length. This has dimensions of frequency. This has dimensions of time. So this is not dimensional, adimensional. Or dimensionless. As it should be, angles are dimensionless. Angles are ratios between two lengths. Right, so they are dimensionless. This has the correct dimensions. This has dimensions of velocity. This has dimensions of 1 over time. So the whole thing has dimensions of length. What is x prime of t? X prime of t is minus omega naught x naught sine omega naught plus v naught cosine omega naught. Which is great because at t equals 0, that is x naught because this is 0. And at t equals 0, this is v naught. So that is good. Let me square x of t. Well, it's gonna be x naught square cos square omega naught t plus v naught square omega naught square sine square of omega naught t plus 2v naught x naught omega naught cos omega naught t sine omega naught t. Let me square x prime of t. So that is equal to omega naught square x naught square sine square of omega naught t plus b square cos square omega naught. There is a problem. You can see that the problem is I forgot the omega naught here. Oh no, I didn't. Good. So b naught t plus, which is in fact a minus twice this times that. So minus omega naught x naught v naught. Sine cos. There is a problem here, and there is a 2. So this omega naught, I think, should be divided. So these two cancel each other out when I add them. So I need to find a mistake. Oh, yeah. Yeah, it has the correct dimension, so square it has to have this times that. Yeah, that is correct. Oh, I see. Right. You know, I think that what I'm going to do next, now that I see it, I'm gonna divide this by omega naught square. So I'm gonna divide this by omega naught square now. So this divided by omega naught square, and this divided by omega naught. And then you can see that I made it work, finally. So I'm gonna add these two together, x squared plus x prime squared divided by omega naught square. And then I can add them together because this has dimensions of 1 over time squared and this has dimensions of 1 over time squared. So the only dimension surviving is L squared, which is the same as that. So everything is good. So let's see what do we get when I add these two together. So I get x squared, cos squared plus sine squared. So that is x naught squared, cos squared, omega naught t plus sine squared, omega naught t. Now plus v naught squared, cos squared plus sine squared. Minus this plus 0. So guess what we got? X squared plus 1 over omega naught squared x prime squared is equal to x squared naught plus v naught squared. Mistake somewhere. This has to be divided by omega naught squared. I think. Otherwise it won't work. Yes, there it is. Sorry. Sorry, I forgot that stuff. That's the equation of an ellipsis. So it's an ellipsis in phase space. Now, I can graph this for you. So that is the equation of an ellipsis. The kind of shape of the ellipsis will be determined by x naught and v naught, as well as omega naught. So let me show you, right? So if I go now to finish the class, right? I go here and I show you this. Oh, I always make the same mistake. I show you this stuff, no, this stuff. Oh, what am I doing? This stuff, right? So we can actually do the thing, do the deed, right? So now I don't want to manipulate this plot, right? That's just the solution. What I want to do is to manipulate a parametric plot. I'm gonna have to take the derivative of this with respect to t. So I'm gonna go and define here this. So I'm gonna put here this and this stuff in here. I'm gonna call this prime. And that is gonna be equal to the derivative of this. But I have to put it like this. With respect to t. And you have here the derivative. So it has solved the equation, stored the solution as a function of frequency, amplitude, and initial velocity. Compute the derivative of that. Now, here I'm graphing the solution. I could have graphed both the solution and its derivative together. Let me do that now, so you can see it. So this was called this prime. And now that should show both the function and its derivative. And you can see that their frequency changes together, right? And x naught, and look, if I screen exchange v naught, the derivative is gonna increase, right? Do you see it increasing? How the derivative, which is the yellow curve, will increase. Maybe I should put a plot legends here. Plot legends expressions. And you can see there the expressions, right? They are changing the frequencies, they are changing the different things. And of course, this to, kind of change the slope. Now the slope is maximum, and then it's gonna kind of, here, right there is maximum the slope. So I hope you're seeing this, I hope. Yes, probably. Not very well because I'm in the middle. So let me just like get myself out of the middle. Although I'm not gonna be looking in the correct direction. So finally, let me just graph the parametric plot, and then I will show you what happens when we put this. So I'm gonna put as x-axis my x, and in the y-axis I'm gonna put the x prime, and that's gonna give me a parametric plot that you can see here. Now when I change x naught, right? If I make it larger, you can see that now it's a curve. If I make it with v naught, it's gonna be more like an ellipsis, I think. Now this changes just the number of things. So now you can see that it's kind of an ellipsis once I change it. And it depends on how you put it, right? So you can see maybe I should put aspect ratio 1 here. So we don't know for sure, right, that it's an ellipsis or a non-ellipsis. Right? So that's a circle, I think. If I increase, it's still a circle, but now it's an ellipsis. Ooh. You can see it's an ellipsis because this is -1, but it still looks like a circle. What shall I do? Maybe specify a plot range. So you can see it's difficult to see that whether it's an ellipsis or not. You know what we can do? What we can do also is to do it in Desmos. So if I plot I'm gonna define some f of t. It's gonna be my displacement. It was x naught cos of omega wt plus v naught divided by omega times sine of omega t. And put all of this. And now I can change x and w and v naught. But now I can also make a parametric plot like this, f of t, f prime of t. And I can just take out these curves, and I have put t from 0 to 2 pi. Then I will have a full 2 pi. Yes. Now you can see it's an ellipsis. If I change it, I put it down to a circle. W doesn't really matter. V changes the ellipsis too. Right, if I put V equals 0, then if I put x naught equals, oh, this looks like an ellipsis still. Is it correct? X naught equals 1. Ooh. Was this omega or omega squared? I don't recall. No, it must be omega. So if I put omega equals 1, then it is a circle. And then as soon as I start to move, this will keep it a circle. But once I kind of like do, it's still a circle. Right? But if you change omega, then right, you will have to find the circle again. Right? Less than 1 takes longer, so it takes longer than 2 pi. Let's put 8 pi. Another interesting thing is to see how this particle moves, right? This particle will move like this, look. I'm gonna put it in here, a point. I'm gonna put it f of s, 0. And I'm gonna add a slider for s. And you can see there the point, right? This is how it moves. Now this is too short, so it should go between 0 and 100. Maybe in steps of 0.001 or something. Let's see. Moves too fast. Let me make it move slower. Maybe the particle needs to be made larger. Done. Yeah, the particle is not very well seen. Do you see it in there? I wonder if you can see it. It's that blue particle there. Right. So that's how it moves, right? You can change the parameter. So if I increase omega, it's gonna go faster. Now it's going all the way around, so probably I should put it there. I wonder if I can make the particle larger. Oh, yes. Points. 4. And now plate. So it's difficult to see, but there it is, the particle oscillating. And that's how it oscillates. Now, how to understand the phase space, right? How should one understand this phase space? Done. This thing here. Well, one thing I can do is to actually graph also the velocity moving, right? Having something like this, but instead of having that, I'm gonna put f prime here of s and a label. Now that is moving around. It's difficult because it's green, so I'm gonna have to change the color to something else. Maybe red or yellow. Let's try with yellow. And then we have to make it go slower as well. And then we can also put the other thing. We can put this look here, but maybe here just put 0. So now you have 3 particles, and it's very difficult to see. But you can redo all that I did in Desmos, right? What you have is x of t oscillating horizontally, b of t is horizontal oscillating vertically, and x of t, v of t, x of t, x prime of t is moving along this thing. And as we change the parameters of the model, we can deform this trajectory into a circle, into an ellipsis, and stuff like that. So that axis is the velocity axis, that axis is the position axis. The real particle is this particle, oscillating in time. This axis shows the velocity, moving, and once you combine those two motions, you get an invisible particle that is moving around here. Oh, there it is, I can see it now. It's that one that is moving, it's moving like this. It's that one that goes around there, moving like that, right? It's a difficult thing, you know, it's a huge endeavor to be able to understand all of these derivations, right? And you can see that those derivations have been pretty long, right? It's kind of like a full long thing that we have covered. There are 3 things that we have achieved. One is we have derived the equation, the harmonic oscillator equations from Newtonian mechanics that led us to a differential equation. It's second order, linear, homogeneous, autonomous. You have to put 2 initial conditions, 2 constants of integrations that are needed to cancel out 2 derivatives, to undo 2 derivatives and extract your solution out. The way this is solved in practice is through a process in which we are guessing a solution, an exponential solution, thereby transforming that equation into an algebraic equation for the exponent. So this happened here, right? This happened there, guess a solution, right? And if we do that guess, then the condition for that R, right, is gonna be this condition here. That will be your condition for the R, right? And then you solve for R, that tells you the frequency of your motion. How long it takes for your particle to complete a loop in phase space, or come back to your original position in real space. 1 period, 1 period, 1 period. And the period, of course, is the same for the derivative. 1 period, 1 period, 1 period, right? So you solve for that. That's called the characteristic polynomial equation. Then those R's gives you those solutions, and there are 2 possible R's, so you have 2 possible solutions. You have cosines and sines, or positive exponent exponentials and negative exponent exponentials. Then mix those up as a linear combination. You have your full general solution. Use your initial conditions, you have your particular solution. What we are graphing here is a particular solution. But when we computed this stuff in here at the top, right, this stuff in here, that stuff is the derivation of the equation of these ellipses from first principles. So, you know, I don't want you to learn a procedure. The procedure is as follows. Get that equation, transform it into a characteristic polynomial equation, find the roots of the characteristic polynomials, put them in exponentials, right? There is that procedure. Here we have done that once and for all. And then you have this, again, another lesson. I haven't used a single number. The numbers at the end. I solve my equation in general. I derive formulas for all of these ellipses. Whatever boundary condition, whatever B naught, omega naught, x naught you have, that's the equation of my ellipses in there. If I put particular values, that equation will turn into the equation for these ellipses. If I change those sliders in Desmos, I will deform these ellipses according to this equation. You can see the ellipses, the equation for the ellipses depends on omega naught, on X node and B node. When I change those, I'm changing the ellipses. The ellipses encodes the entire dynamics of the system. A harmonic oscillator is a bunch of ellipses in phase space, right? So if you have gone through these derivations, right? And by the way, I don't know if you know this is gonna be kinetic energy plus potential energy, right? So yeah, that is gonna be the energy of your system. That is the kinetic energy, and that is the potential energy. Particularly once you put factors a half and stuff like that on front, right? That is the total energy of the system is conserved. Why is it conserved? Well, because it's an autonomous system, right? So if you are studying this discipline, these differential equations, energy conservation, right? If you look at it from the perspective of autonomous differential equations, you got it in here, right? There is gonna be this quantity that's gonna be conserved. As these ellipses, as this particle moves, right, through these ellipses in phase space, as time goes by, the particle describes a trajectory. That trajectory is that ellipsis. That ellipsis is characterized by this thing being constant. So this stuff is equal to this stuff at no matter the value of t, right? So as the particle is moving, this thing is being constant. This thing here is being constant. The velocity square plus the position square with correct divisors, right? That is a constant of motion. That is gonna be very close to the total energy, total mechanical energy of the system, the sum of potential energy and kinetic energy. The potential energy is 1/2 of omega naught square x squared. So if you multiply this by omega naught square and divide by a half, then you get the expression for the total energy, right? Provided that the mass is 1. Yeah. In any case, that was my lecture on the simple harmonic oscillator. I will give you another lecture on the damped harmonic oscillator. And I will give you, maybe, hopefully, lecture on forced harmonic oscillators with Laplace transforms. So there is one extra lecture about harmonic oscillators. Good luck. Watch the lectures, don't leave it for the last day of course. Going through this will help you learn the stuff that comes later. So you should do it. But if you are watching it, then you are already doing it. And if you are not watching it, then you're not listening to this. So what am I doing? Good luck. Enjoy.